The universe is often perceived as a realm of eternal, unchanging lights, a celestial clockwork where stars follow predictable paths for billions of years without interruption. This perception of stability is occasionally shattered by events of such profound violence and scale that they challenge the foundations of stellar and planetary evolution models. In September 2024, the astronomical community was alerted to a localized crisis of luminosity in the constellation of Monoceros, where a star designated as J0705+0612, also known by its survey designation ESASSN 24FW, began a precipitous and anomalous decline in brightness. Located approximately 3,000 light-years from Earth, this solar analog star had remained photometrically stable for over a decade of observation by the All-Sky Automated Survey for Supernovae, ASASSN, a network of robotic telescopes that monitors the entire sky daily for transient events. Without warning, the star's visual magnitude collapsed, its luminosity dropping to a mere 2.5% of its baseline brightness. This was not a subtle flicker. It was a factor of 40 reduction in light, as if a massive, opaque shutter had been drawn across the face of a sun identical to our own. For 254 days, nearly 9 months, J0705+0612 remained in this state of deep occultation, presenting a profound mystery to the astrophysicists at Johns Hopkins University and their global collaborators who were witnessing what appeared to be the disappearance of a mature star. The photometric analysis of J0705+0612 reveals several critical parameters that define the magnitude of this cosmic cataclysm. Most notably, the dimming factor reached an extreme level of 40 times the baseline brightness, representing a 97.5% reduction in starlight due to the immense optical depth of the debris cloud. This state was maintained for a duration of 254 days, or approximately 8.5 months, which indicates a low orbital velocity characteristic of an object residing in the cold, outer regions of the planetary system. The spatial scale of the occulter is similarly staggering, with the cloud spanning a diameter of approximately 200 million kilometers, or roughly 1 astronomical units, a structure larger than the entire orbit of the Earth around the Sun. Located approximately 3,000 light-years or 1,000 parsecs away within the Milky Way, the system is mature, with an age exceeding 2 billion years, signifying that the destruction observed is not a remnant of the star's formation but a late-stage reconfiguration of its planetary architecture. The nature of this dimming immediately ruled out intrinsic stellar processes. G-type main sequence stars, the classification into which J0705+0612 falls, do not simply cease their nuclear fusion or develop star spots large enough to block 97.5% of their surface area. Pulsational variability and limb darkening effects also failed to account for the U-shaped profile of the light curve, which displayed a flat, prolonged minimum characteristic of an extended, structured occulting body rather than a point source stellar companion. The duration of the event, combined with the slow ingress and egress of the shadow, suggested that this massive body was not an interstellar intruder but a gravitationally bound component of the J0705+0612 system, moving at a relatively slow orbital velocity in the colder, outer regions of the planetary architecture. The implications of such a discovery are both terrifying and scientifically transformative. If a stable, 2-billion-year-old solar system can undergo such a radical reconfiguration, it suggests that the quiet maturity of our own neighborhood may be an illusion of timescale rather than a guarantee of safety. The sudden appearance of a debris cloud of this magnitude in a mature system contradicts traditional protoplanetary disk models, which posit that primordial dust and gas are cleared within the first few million years of a star's life. Therefore, the material blocking the light of J0705+0612 was not a remnant of the system's birth, but rather the recycled remains of its maturity, a rejuvenation paradox where an old star suddenly displays the dusty, infrared signatures of a stellar nursery. To unravel the mystery of the vanishing star, astronomers turned to one of the most powerful forensic tools in modern science, the Gemini High-Resolution Optical Spectrograph, or GHOST, mounted on the Gemini South telescope in Chile. While standard photometry can track the depth and duration of a dimming event, spectroscopy allows scientists to peer inside the shadow itself, breaking down the starlight that filters through the debris into a detailed chemical and physical map. In March 2025, while J0705 plus 0612 was still in the depths of its 254-day occultation, the GHOST instrument was deployed to capture a high-resolution spectrum of the star's light as it struggled to pass through the intervening cloud. The resulting data provided a breakthrough that exceeded all theoretical expectations. Instead of the cold, rocky dust one might expect from a simple asteroid belt, the GHOST data revealed the unmistakable signatures of vaporized metals, the astronomical term for elements heavier than hydrogen and helium, specifically iron and calcium. The spectroscopic characterization provided by the GHOST instrument identifies several distinct chemical signatures that reveal the physical interpretation of the event. The detection of gaseous iron and calcium through absorption lines serves as definitive evidence for the sublimation of a planetary metallic core and silicate crust, respectively. The measured blue shift of these spectra, indicating a velocity of 27 kilometers per second, points toward a rapidly expanding debris cloud or a magnetized outflow driven from the collision site. Furthermore, kinematically complex sodium deabsorption lines suggest a multi-layered gas structure with significant density variations, while the presence of a broad hydrogen alpha line indicates intense interactions between the inner disk and the host star. The precision of GHOST, capable of reaching a spectral resolving power of 76,000, has effectively turned the Gemini South telescope into a laboratory for studying the immediate aftermath of a giant impact. These winds are not merely drifting, they are being actively driven away from a central gravitational anchor. The spectra showed a significant blue shift, indicating that a substantial fraction of the vaporized metal is moving toward the observer at speeds of approximately 27 kilometers per second with respect to the star. The presence of calcium is particularly telling, as it serves as a chemical marker for the destruction of a planetary crust, while the iron points toward the catastrophic disruption of a terrestrial planet's core. This data confirms that J0705 plus 0612 is not being occulted by a natural feature of stellar evolution, but by the literal vaporized remains of shattered worlds, a ghostly signature of a planetary system in the throes of a massive structural reconfiguration. The detection of these elements in a gaseous state at a distance of 14 astronomical units from the host star presents a thermodynamic conundrum. In the frigid environment of the outer solar system, roughly 1 billion miles from the primary sun, iron and calcium should exist exclusively as solid components of planetary crusts and cores. Their presence as a vapor implies a high-energy origin, specifically an event powerful enough to reach the sublimation temperatures of silicate rock and metallic iron. GHOST sensitivity allowed for the detection of multiple metals within the cloud, exceeding initial expectations and providing a unique window into studying hidden phenomena in distant star systems. The revelation of metallic winds in 2025 was just one piece of a much larger puzzle. To understand whether this cataclysm was a singular event or a recurring phenomenon, astronomers reached back through time, utilizing the digital access to a sky century at Harvard, or DASH. DASH is a monumental effort to digitize over 500,000 glass photographic plates held at the Harvard College Observatory, spanning the years 1880 to 1985. These plates represent a century-long record of the sky, captured by generations of astronomers who could never have imagined the computational power that would eventually be used to analyze their work. By searching these digital archives for the coordinates of J0705 plus 0612, researchers discovered that the 2024 disappearance was not an isolated incident. Identical dimming events, characterized by the same depth and 9-month duration, had occurred in 1937 and 1981. The historical record of J0705 plus 0612 is defined by a recurring shadow that has reappeared across a century of astronomical observations. Archival data extracted from the Harvard College Observatory's photographic plates show that an identical dimming event occurred in 1937, lasting for approximately 9 months and showing the same depth of 4 magnitudes. A second occurrence was recorded in 1981, exhibiting the same photometric profile and duration. The current 2024 event, documented by ASCSSN and the Gemini South facility, lasted 254 days with a magnitude drop of 4.12. These three data points establish a remarkably stable orbital phase and periodicity of approximately 43 to 44 years, or 16,000 days, allowing for the precise prediction of the cloud's return in approximately mid-2068, which will likely last another 250 days. This historical data establishes that the debris cloud is not a transient intruder passing through the system, but a stable structure anchored to a massive, orbiting object. Using Kepler's third law of planetary motion, which relates the orbital period of a body to its distance from the star, astronomers calculated that the mystery object anchoring the cloud resides at a semi-major axis of approximately 12.4 to 14 astronomical units. This placement puts the site of the collision in a region analogous to the space between Saturn and Uranus in our own solar system, a vast, cold frontier where the stability of planetary orbits was previously thought to be absolute in a mature system. The fact that the cloud remained opaque and gas-rich across three recorded events spanning nearly 90 years presents a significant thermodynamic challenge. Normally, vaporized metals in the vacuum of space would be expected to cool and condense into microscopic smoke or dust particles within a few years as the material radiates its thermal energy. The persistence of the gaseous signatures from 1937 to 2024 suggests that either the initial impact was so energetic that the material has yet to reach a thermal equilibrium, or that there is an ongoing mechanism, perhaps a cascade of secondary microcollisions within the debris disk that maintains the high-entropy, vaporous state of the iron and calcium. What kind of object could maintain a 200 million kilometer cloud of vaporized metal for nearly a century? The most robust physical framework for explaining the J0705 plus 0612 event is the synestia hypothesis. Proposed in 2017 by planetary scientists Sarah Stewart and Simon Locke, a synestia is a hypothesized type of planetary object that forms when two large bodies, such as terrestrial planets or super-Earths, collide with such high energy and angular momentum that they surpass the co-rotational limit. In this state, the planets do not merely shatter, they vaporize and expand into a rapidly spinning, donut-shaped mass of molten and gaseous rock. A synestia has no solid surface. It is a high-entropy torus with a dense, solid body-like core and a loosely connected outer region that orbits at speeds dictated by the total angular momentum of the impact. This structure provides a coherent model for the J0705 plus 0612 system, explaining the immense 200 million kilometer diameter as the result of the thermal expansion of vaporized planetary material. The synestia model divides the occulting body into several dynamic regions, each with a specific physical state and function. The innermost area is the co-rotating region, which behaves like a high-entropy, solid body-like core composed of hot vapor and molten fragments. Beyond this lies the transition region, a turbulent zone where vapor and liquid droplets interact and generate the three-dimensional metallic winds measured by Gemini. The vast, donut-shaped torus that characterizes the disk-like region provides the massive shadow that obscures the starlight for 9 months. Finally, the exterior atmosphere of the synestia acts as an expanding vapor shell, serving as the source for the detected blue-shifted absorption lines that define the system's spectral signature. The scale of the energy involved in creating a synestia is almost beyond comprehension. For a planet similar to Earth, the energy required to achieve shock-induced vaporization of its silicates and iron core is approximately 10 to the 32nd joules. In a high-velocity collision exceeding 10 kilometers per second, the resulting shock waves reach pressures of hundreds of gigapascals, instantaneously causing the lattice structure of rocks and metals to fail and sublime into a plasma-like vapor. The synestia model is not just a theoretical curiosity, it is a vital link to our own history. Geochemical evidence suggests that the Earth-Moon system formed through a nearly identical process approximately 4.5 billion years ago. The isotopic similarity between the Earth and the Moon, often called the planet's genetic code, can only be explained if they both formed within a common cloud of vaporized material where their compositions could mix and equilibrate at temperatures between 4,000 and 6,000 degrees Fahrenheit. By observing J0705 plus 0612, we are witnessing the Hadean stage of a planetary system in real time, a period of cooling and contraction that will eventually result in the birth of new solid bodies from the ashes of the old. The synestia in J0705 plus 0612 is a short-lived state on a cosmic scale, likely lasting only centuries before collapsing back into a molten planet and its attendant satellites, making our current observation a rare privilege in the timeline of the universe. This metamorphosis of planetary material, from solid to vapor soup and back to solid, is a fundamental process in the early life of many planetary systems. The most unsettling question raised by J0705 plus 0612 is why such a violent collision occurred in a system that had been stable for 2 billion years. Traditional models of planetary dynamics assume that once a system passes through its early formation phases, the orbits of its planets are locked into a state of long-term equilibrium. However, the discovery of a catastrophic impact in a mature architecture suggests that the universe is never truly static. This late-stage instability is often the result of secular chaos, a process where subtle gravitational perturbations between planets, accumulating over hundreds of millions of years, slowly pump up the eccentricity of an orbit. Even a system that appears perfectly balanced can harbor secular resonances, where the precession frequencies of two planets match, leading to a chaotic exchange of angular momentum that eventually forces their orbits to cross. Several hypotheses regarding the nature of the secondary gravitational anchor are currently under evaluation, each supported by specific mass ranges and observational markers. If the companion is a massive exoplanet between 5 and 13 Jupiter masses, the cloud would be classified as a circumplanetary disk, consistent with the Hill radius constraints required to hold the debris together. Alternatively, if the object is a brown dwarf between 13 and 80 Jupiter masses, it would explain the M8-type spectral features and enhanced infrared excess observed in the near-infrared spectra. A third possibility posits that the anchor is a low-mass M-dwarf star exceeding zero. Solar masses, specifically around zero. Solar masses, suggesting a binary configuration with a circumsecondary disk. Regardless of the exact mass, the 4% polarization and blue-shifted winds strongly suggest that this anchor is a highly magnetized body capable of driving the observed outflows through a magnetocentrifugal mechanism. The system exhibits signatures of a magnetocentrifugal wind, a phenomenon where the magnetic field of the secondary object couples with the ionized vapor of the collision debris, accelerating it outward like a cosmic slingshot. Observations from the Gemini and OSU teams revealed strong polarization, up to 4%, and blue-shifted spectra, which combined imply a magnetized wind flowing away from the circumsecondary disk. This interaction between gravity, heat, and magnetism creates a dynamic environment that defies the frozen state we typically associate with old star systems. This magnetized outflow likely plays a critical role in clearing the metallic vapor from the system, eventually allowing the synestia to cool and condense into new, solid planets. Such mechanisms explain why we see sweeping winds of iron and calcium rather than a static, stagnant cloud of dust. The presence of a massive secondary object, estimated to be at least several times the mass of Jupiter, acts as a gravitational anchor, essential to prevent the 200 million kilometer cloud from dispersing into the interstellar medium under the pressure of the host star's radiation. As J0705 plus 0612 returned to its normal brightness in May 2025, the metallic cloud began the next leg of its 44-year journey through the dark. For the next 4 decades, the debris will be largely invisible to our current generation of optical telescopes, as it is no longer silhouetted against the host star. This creates a temporary silence in the data, but it also sets a definitive timer for future generations of astronomers. When the cloud returns in 2068, we will likely observe it with instruments of unimaginable precision, perhaps the extremely large telescope or space-based interferometers that will be able to resolve the mystery object directly and track the cooling and clumping of the debris as it forms new moonlets and protoplanets. The study of J0705 plus 0612 has effectively transformed the star from a distant point of light into a dynamic laboratory for forensic exoplanetology. The rejuvenation paradox of J0705 plus 0612 is best understood through a comparison of observational markers with those of young stars. While young stars typically exhibit high infrared excess from primordial disks, J0705 plus 0612 displays a similar signal created by the recycled material of a planetary collision. Young stars show strong lithium absorption, a marker that is notably absent in J0705 plus 0612, confirming its mature stellar age of over 2 billion years. Furthermore, while accretion drives the hydrogen alpha activity in young systems, the strong and transient activity in this system likely results from the gas interaction within the occulting disk. Finally, the dust composition of J0705 plus 0612 is uniquely metal-rich and vapor-dominated, signifying the destruction of a terrestrial mass core rather than the carbon-rich or icy material found in primordial envelopes. Ultimately, the discovery of metallic winds in J0705 plus 0612 shows us that the cosmos is an ongoing story of creation, destruction, and transformation. The atoms in our own bodies, the iron in our blood and the calcium in our bones, might once have been part of a similar cosmic collision, vaporized into a metallic wind before condensing into the pale blue we call home. As we look toward the 2068 return of the J0705 plus 0612 cloud, we are challenged to return to the system with better tools to see what has become of its shattered worlds. Whether this event represents the birth of a new planetary architecture or simply the final whimpering of a dying world, our ability to understand the mangled information of a shattered world makes us something truly special in our insignificance. The universe does not always follow our desire for order, but it provides a persistent record of its changes for those willing to look through the archives of time. The analysis of the 254-day occultation of J0705 plus 0612 leads to the following conclusions regarding the state of the system and its broader implications for astrophysics. First, the event represents a definitive observation of a late-stage planetary cataclysm in a mature system, confirming that mature architectures are not static, but remain subject to catastrophic reconfigurations billions of years after formation. The detection of three-dimensional metallic winds composed of vaporized iron and calcium represents a landmark in forensic exoplanetology, allowing for the direct chemical sampling of destroyed planetary interiors through high-resolution spectroscopy. Second, archival data from the 1937 and 1981 dash records identifies a persistent 44-year periodicity, confirming that the debris is anchored to a massive, orbiting secondary object roughly 14 astronomical units from the primary star. The integration of the synestia hypothesis offers the most comprehensive physical framework for the event, explaining the immense 200 million kilometer scale and high entropy of the debris cloud as a transitional phase between a giant impact and the eventual reformation of planets. Furthermore, the discovery of potential magnetocentrifugal acceleration within the metallic winds suggests that magnetic fields play a critical role in the dispersal and cooling of collision debris, a factor that must be included in future models of planetary formation and destruction. Finally, the rejuvenation paradox observed in this system implies that a significant number of young stars in current catalogs may actually be older systems undergoing similar late-stage instability, suggesting that the frequency of large-scale planetary collisions in the mature universe is higher than previously estimated. The return of the occulting structure in 2068 will provide the ultimate target for the next generation of astronomical observation.